So Matt, I know we've done this before, but still, like, can you introduce yourself for the audience?
Yeah, no, it's nice to be here. My name's Matt Jordan. I'm a strength and conditioning coach from Canada. Formerly worked in Olympic sport and professional sport for about, almost 20 years. Worked under some really prominent Canadian strength coaches. Worked very closely in my beginning years with Charles Poliquin, which I'm sure some of your listeners will probably know his name, but there was some good people at that time in Canada that were influential in my development. And then along the way, got my PhD in medical science, did some leadership roles as a director of sports science, sport medicine for some of our Olympic teams. Currently do quite a bit of consulting with professional athletes and teams, and I'm a researcher at the University of Calgary. So I've got a strength lab and a team of grad students, and we're tackling the problem of knee injuries and rehabilitation in collegiate sport athletes. And so looking at how we can use a kind of like a biopsychosocial approach to help get athletes back to performance after they suffer injuries like ACL rupture.
Nice, nice, nice. And I also noticed like you help a lot of like ACL return to play like paper.
Yeah,
Am I right?
yeah, that's correct. Yeah, that's a big area of interest.
Nice, nice. So I know you're involved with like plantiga. Am I pronouncing it right?
Yeah,
Plantiga.
yeah.
The development of plantiga. So can you like talk a little bit about this project?
Yeah, sure. I mean, yeah, in a nutshell, I mean, happy to talk about it because it's an interesting story how, I was sort of initially approached. It was about the time where I was publishing quite a bit on the dual force plate asymmetry testing. And I got a call from the CEO of the company, and he said, "Hey, listen, we are doing an insole, and we're wondering if there would ever be any value in measuring asymmetries on the field of play or on the court." And I was like, absolutely. I was like, that's the biggest blind spot is that we have, all this testing we do in the lab. Lots of people didn't even do that at the time. It was mostly just sort of like time and, kind of get a feel in your gut that somebody's ready or not. But I was like, once the athlete gets on the field or the court, there's like no way to know how they're progressing. And we'd had lots of data from single athletes coming back to sport after injury where you would see them at like the return to play phase, and then about 2 to 3 weeks later, and they would like go backwards. And a lot of times people wouldn't catch that because it would be, you wouldn't be able to know. You would just assume they were stable and that their function was improving. So that was now going back, yeah, almost 7 or 8 years ago, and I started working with a company. Interesting development was about probably about I don't know, maybe a year or two in, the company really began to sort of grow in the space of athlete monitoring, and it was more than just now an asymmetry testing tool. It was like, hey, we can monitor load with this. We can actually potentially initially was like we can replace GPS because the problem with GPS is you've got the accelerometer in the spine or in the thorax, and you're sort of measuring the athlete move around the field, and you can get, distances and speeds and whatnot, but it's really hard to know the mechanical load at the foot. And we think that's a big contributor to obviously that lower load, lower limb mechanical loading is a contributor to overuse injuries and injuries in general, and obviously very important for performance. And so we said, well, this is going to be more than just an asymmetry testing tool. It's going to be a good load management tool. And so, yeah, fast forward to today, and the company's just passed the NBA validation, which is really cool because the NBA requires all wearable companies to do third-party validation to basically be approved to be used with the NBA teams. So it's a very rigorous process. And so third-party university institution validated Plantiga against motion capture and force plates to be able to make sure that it was accurate, and it passed with, surprising results. We also have had numerous university partnerships, John Cronin being an example, that have used us for various research studies, and actually it's been also really promising findings there. And so today it's now part of the NBA's venture capital sort of a company program where we're going to be tracking WNBA athletes. We're being used by a whole whack of professional teams. And I guess the aspirational goal is Plantiga lets you measure step-by-step asymmetries and mechanical load at the foot and is able to provide a whole new lens on athlete monitoring on field and on court and on ice that we currently have not been able to do before. So we can really see these things at high precision, high accuracy, and understand how asymmetries and load are being changing over time as athletes adapt, either with training as a preventative thing for injury prevention or as a part of rehab.
Cool, cool. So for those who haven't like looked into Plenty, can you like walk us through how exactly does it check like the asymmetry and
Yeah,
biomechanic
yeah,
load?
totally. So simply put, I've got a sensor here. So the sensor is a little wafer, and it goes in. The important thing is it's not an insole. This wafer can go in any piece of footwear. So it can go in a custom orthotic. It can go in a shoe. It can go in one of the. We partnered up with an athletic insole company that actually makes an orthotic that will fit this. But essentially, it pops in the shoe. You immediately, once you're in there, it's virtually undetectable because it's so thin. You press record, and then essentially it's collecting data. And what's cool about Plantiga is because it's built on some AI, their algorithms can do what's called automatic movement recognition. So it essentially says, here is when you're running, here's when you're walking, here's when you're jumping. Eventually, it'll be here's when you're changing direction. And so at the end of, let's say, an hour on court practice, you're essentially getting this whole picture of the activity with all the step-by-step mechanics over the course of the activity. And then Plantiga essentially it's got a really powerful web interface. So it goes from that step-by-step acceleration load, which you can visualize, to your activities that you care about inside of that. So it doesn't pick up when you're on the court. Let's say you're on the bench and shaking your knees around. It's actually only picking up when you're running or jumping or running. So it's very good at knowing what you're doing. And then it's able to generate, in addition to obviously all the step-by-step analytics, it's able to generate kind of an actionable report. And so we hone in on what we call our tier one measures, which are basically the mechanical load, which we call athlete load, which is essentially the XYZ acceleration basically at touchdown and toe off. So basically impact and push off in running and jumping, which is a good measure of deceleration and acceleration load. So that's really cool. Like you can really see the deceleration component of human movement. We can look at the asymmetries in that. We can also look at the asymmetries in our tier one measures like ground contact time, foot speed, stride length. And then moving one step below is you can now look at speed. You can look at we call them movement maps, but it's like a map of how the person moves. And it's, so sort of like tier one measures are for the people who are like, hey, I want to monitor load and asymmetries and I want to be able to make an actionable decision. Tier two measures are for the bit of the nerds. That's like, hey, I want to dive into performance here and really understand what's going on. That's where I spend a lot of my time because I want to see these more granular measures. And then tier three measures are for like the researchers and for people who are going to say, hey, we want to take these data now and really understand the complexity of human movement. And so it's a pretty cool, powerful system for all levels. Like whether you're, hey, I want a turnkey solution, I just want a number, or hey, I'm a proper scientist here, and I'm really going to want to use this tool to explore and expand on human movement. And it's, flags it, sort of tells you relative to a reference database what your norms are. And it also will flag you relative to you. So as you change over time.
So does it do like is it like they track their pressure on the foot? Is it like that?
Oh, well, I mean,
Like
so,
pronate eversion, that kind of stuff?
yeah, so you think about the same technology that's in your phone that's sensing, the like when you turn your camera and it like adjusts the screen automatically. Or you adjust so you're looking at Safari and you move it and it like plops. It's called they're called inertial measurement units, and these are them, right? So these things are able to measure, they've got a magnetometer so they can kind of sense direction. They've got a gyroscope so they can measure, position. And then they've got an accelerometer, which is measuring this. And so a pressure sensor is kind of like, you can think about it sort of like a force plate, but it's telling you where in your foot you're pushing. But the only time you are measuring anything with a pressure sensor is when your foot's on the ground. So there's a ton of information with a pressure sensor that you can't get, like how the foot's moving through space, how you accelerate the foot down, how you create movement is like completely missed with a pressure sensor. Um, and the other thing about pressure sensors is they're super bulky, so they're not comfortable in the shoe. They are generally very fragile. So if you have a high level athlete who's doing like 10 extremely high demand change of direction movements, these things tend to break. And the third thing is that their battery life, they're super hungry for power. So you couldn't record a practice. You'd have to have a very careful experimental scenario where it's like a researcher's controlling this, which basically is a little bit more real world, but it's probably better just to use a force plate and a motion capture system. This is a true wearable tech and it's measuring your motion. So it's when you think about on-field play and performance, to know when somebody's changing direction, jumping, walking, backpedaling, sprinting, you would not be able to know that with a pressure sensor. With this, you can measure all the intricacies of human movement. So this is capturing all the movement that happens as your foot moves through space, how it accelerates down towards the ground at impact and pushes off, which is going to be it's actually highly correlated with forces. So your impact acceleration and toe off acceleration have a high predictive value relative to the forces that you would measure with a force plate. So it's not forces, but it's correlates very well with mechanical loading that we assess with force plates. And so you take this all together, and it's like it truly provides a picture of human movement. And so I think it's a way better technology for athlete monitoring because we get the motion, we get the full picture, the battery life, it can go for 8 hours. It's extremely resilient. Like this thing will not break with high mechanical loading. And so, you can safely put this in the shoes of football players and test, 90 of them in a session and be able to, essentially quantify load and asymmetries and performance over the course of a practice or a game.
That's correct me if I'm wrong. So it's kind of like when we talk about like I know like I'm gonna use it like I know there's like biomechanical lab they have like maybe 30 like 10 meters 15 meters of 3D three-dimensional force plate and
Yeah.
you also combine it with motion capture. Is it like that?
Well, that's what we do in the lab. And that's what this is now validated against. So if you are thinking, okay, I'm in a lab and I want to measure stride length and I've got to put on markers and use force plates and I have to be able to go back after and it takes me 4 hours to bring the data in and crunch the numbers and extract the data. And even markerless, right? Like you're still in a confined space. You're not on the field. You're like in a lab setting where you're like, okay, participant, ready, 3, 2, 1, run. And the person runs. Okay, stop. Okay, walk back. Let's go look at the data, see what happens. That's lab-based testing that you just described. This is validated against lab-based testing, but I put these in your shoe. I press start and I say, go do your practice. And you're like, okay. So you're out there, you're warming up, doing some jumping jacks, or I don't know, you're doing some burpees or some stretches. It doesn't care about that. It's like, well, that doesn't seem like interesting activity. And then all of a sudden you're like, okay, now I'm going to go start doing my warm-up accelerations. And so you're on the field and you start running along and you do some jumps at the end, maybe. The algorithms say, oh, this is all stuff we care about because now we know he's running, he's jumping, like this is the stuff that athletic, performance is based on. And now you're out playing in the game and now you're doing like actual, loading. And so it cares about that too. And then at the end of your practice, you're going to walk back to the dressing room and you want to know, like, let's say how your walk patterns have changed before and after practice. It's going to say, here's your walk before and after. And the cool thing about this is there's no person like me saying, hey, could you do a walk now? You just are doing it and I'm just recording it on this. And then you're done your practice, I upload it, and then I've got the entire session all broken down with metrics that have been validated against the lab-based measures. But now this was captured in the real world. Sometimes we call this the Hawthorne effect, which is just by the act of me measuring you, it changes how you move. So just by you knowing like, hey, Matt's going to take a jump measure on me today, you're going to change and alter your movement strategy because you're being observed. This is now like it eliminates that. So you are just doing your thing, and I'm able to measure exactly what you do on the field, on the court, on the ice when you're practicing, playing the game, warming up, cooling down, walking to and from the dressing room, walking on the field and the sidelines in your when the other, when the defense is on. So it's a way that we are truly able to extract accurate and precise data about human movement in the real world, but tailored to athletes. So, the technologies that are out there that can do something similar, like they can't handle a 250-pound lineman doing a hard change of direction. They break. Or it's like, well, we need to have 4 hours of data collection because it's a long day and a long practice. Can't do that. We need it to be comfortable and like you can't feel it. Well, no, we can't do that because our sensors are these big insoles that are super bulky and they don't fit in a cleat. So all of those are problems with the current technology. And this comes along and it's like, hey, you just put that in. We've got a validated technology against all the gold standards, so you can trust the data. And now you literally don't have to worry about anything. You don't have to be like hitting record buttons and stuff. It's just like press start and away you go, and you got that measurement. I also think it's kind of neat too because sometimes in scenarios like I'm working on a couple of rehabs right now where the athlete's not located with a performance team. So I've got one athlete that's coming back, and it's coming back after a pretty severe knee injury. So it's a chondral injury, and it's been a long, long road for this particular individual. They've got a whole performance team who's supporting them and getting them sorted out and all that stuff. But where this comes in is I can help them with their load management. So this athlete can put this inside their equipment in their what shoe, skate, whatever. They can record all their sessions, and then we can work together to monitor their asymmetries, mechanical load, all those things as they recover, which is really cool because now this connects somebody like me who's an expert in load management and asymmetries and rehab to the manual therapist who's an expert in soft tissue, to the strength coach who's on the floor, to the athlete who's trying to come back. And so we've got a way now that we can all interact on how this athlete's actually moving. It's the question we always ask. It's like, an injured athlete's coming back to sport. It's like, well, how do they look? And you say, oh, I think they look good. Or maybe like they look okay, right? Like I noticed a little hitch in their walk or whatever. How do they look on the field? Well, I don't know. They look like they're moving pretty good. Like it's always qualitative. And so now we have truly a way to objectively measure that.
Man, that's fascinating. I can
Yeah.
imagine that in my mind. That's fascinating. I would love my athletes like wear that stuff.
Oh yeah, it's so cool. And like things that I've always cared about and interested in knowing. So for example, after an ACL injury, I don't know if you've ever seen this statistic, but the um, uh, the prevalence of contralateral knee injuries, so you blow your left knee and then you blow your right knee, is actually uh, surprisingly high.
Yeah.
So we always think about re-rupture, re-injuring the same leg, but the re-injury on the contralateral knee is
Yeah.
like, 20,
Yeah.
20% of them are those. And we don't know really why that happens. Is it because maybe you had the same problem on the other side that contributed to it? Did you not rehab effectively on the actual contralateral side? Is there some change happening? But one idea is that you are constantly compensating and putting more mechanical load through the non-injured side over
Yeah.
time.
Yeah.
And a new sort of understanding potentially of how ACL injuries happen is that it's not just one single big traumatic event. It's that you've been grinding away at that ACL over weeks and months, and it's not keeping up with its remodeling and it's becoming weakened. And then you have that innocuous step and you're like, pow, knee's done, right? And so we're really like, when all of us say, well, like maybe it's fatigue, like there's a fatigue component, not just like central fatigue, but like tissue fatigue, right? Mechanical failure of the tissue that's accumulating, or structural stress, like it's accumulating over time and causing like a progressive loss of tissue quality. I guess what this opens the doors for now is we can really understand how movement changes, let's say from the beginning to the end of a practice, the start to the end of a week, when you're under high pressure and like trying to like, you know, I don't know, run for your life from a defensive line that's trying to tackle you. When you're on court and you've got people watching you and it's a high stakes environment, understanding how your movement patterns have changed from before an injury. Like, are you playing and loading differently after you get back on court? That's another thing that we know with ACL injuries that athletes, about half of athletes make it back to sport, like competition, sorry. Like, so, you know, it's lower than you would think. But of those athletes who get back to competition, like a very high fraction of them show performance loss for years. So it's like you're back, but you never really got back to your like your true level. And you know, we don't know why that happens. And so I think what this technology opens up the door for is how we can better assess this in a real world environment. And you know, it was interesting. I was talking to I work at the Sport Medicine Center at the University of Calgary. It's probably one of the oldest and most well-known community-based sport medicine centers in Calgary, but it's also been on the map for decades as a research institution with some really great researchers who've done very impactful work, and they're very meticulous and careful. And I was talking to the medical director, his name's Dr. Nick Matadi. And you know, Nick's published a lots on these topics, and he's done some really good research over the past, you know, 20, 30 years. And he was saying, you know, when I clear athletes, I don't clear them in my clinic. I clear them by going down to the field and standing there and watching them play with the coach. And that's how I know and clear and give feedback on whether or not we think the athlete's ready to get back. And he's recognizing, right? Like, what can I see in a clinic environment? I mean, I don't know. He's, you know, this athlete looks okay, I guess, doing this body weight squat. But like, what's going to happen when they're on the field and having to make crucial plays and thinking about catching the ball and, you know, and all that stuff? And, you know, I was saying to Nick, I was like, you know, Nick, I sort of feel like one of the biggest missing pieces is how we measure and monitor load for athletes with ACL injury on the field, like as they come back. And you know how that contributes to rehab, return to performance, re-injury, clearance. And you know, his response was like, "Yeah, I couldn't agree more." So I think that there's an awareness that you know it's not just with strength coaches, but we need to have better capture of real world human movement on the field, on the court, on the ice. Like that's where they move. That's where we need to understand and measure what they do. And you know, GPS won't tell you that. They'll just tell you a global marker of what's happening, you know, in terms of biomechanics and well, not biomechanics, even like just the speeds and distances and accelerations, you know, but they don't give you the granularity. Like you can't know on field, do I have a stride length asymmetry? Do I have a ground contact time asymmetry? And even if you do, and I think the technologies might get there where you can kind of predict these things. What's cool about Plantiga is it's truly been pushed through validation. So it is sampling at 400 times a second. Every time the foot hits the ground, it's able to provide very high quality data. So data you can trust. And if I was using GPS and trying to extrapolate down to stride length, or like a wristwatch, right? Where you're like, well, I can kind of see strides and we can probably predict this. As a scientist or a practitioner who's got to make a decision about an athlete, I'd be like, probably doesn't pass the test. Like it's not going to pass the NBA validation. And what's more is they're not going to be wearing wristwatches to do that. Like you need to have this in a shoe away from the body so nobody can see it, nobody can bump it. You know, like that's another big problem with some of the other body-borne stuff. Things get jostled around and it's hard to know what's going on. This is in the shoe away, and you know, I think it really, as I say, it like clears that blind spot that lots of us have sort of felt are, you know, impeding us from really testing athletes after they're hurt.
Nice, nice, nice. So, just to clarify, because it can sense like you move like this, all these.
Mhm.
So, uh, it works for athlete. Well, I mean, for me, in my mind, even it's better than like GPS data. It's because you really track how they land during the sprint. So it's gonna be very helpful for those like who maybe had chance to get like ACL injury or they came back from an ACL injury. So you know how they land, you know probably the biomechanic of a foot to knee to hip. Am I right?
Yeah, I mean, in a nutshell, we are, just to be clear, we're currently not predicting knee and hip kinematics, but that's something that, in our we had a really great team of engineers going back about 2 years ago. And then, like every startup in the world, it was tough times. And so, we are the team got quite a bit smaller, and we have still amazing engineers, but it's just a capacity problem, right? Like you need to have like a team of these people to answer a question like that. And so it was kind of neat that a couple of years ago we were like, hey, I wonder if we can, can we predict what's going on at the knee and the hip? And the engineers were like, totally. So this is something that's in the pipeline right now. That's not something you can do, but what you can do and what you're describing is we can see what's happening in the X, Y, Z plane, right? With the foot, and it's really, really cool. Like you can actually see all sorts of rotational accelerations, and you can like literally carve that out step by step. So
Yeah.
anything at the ankle is like really, those are the like again what I call the tier two, tier three measures. So tier one is we are really, really good at measuring mechanical load at the foot at impact and takeoff. So it's like impact acceleration load and push off acceleration load. You get a side to side difference in high accuracy. You get stride length, ground contact time. You get running speed, running distance. You get really good measures of those and the side to side differences. Tier two, you're getting into some of the measures that are um, probably a little more, like I said before, it's more for the nerds. And then you get down to tier three, which is going to be for like yourself and the scientists who are like, hey, we really want to know the biomechanics, and you can see in tremendous detail with each step exactly what's going on. And so it's a very informative tool to kind of dig into, what an athlete might be hiding. And I always say it's like stuff you can't see with your eye, right? So that's why the force plate thing was always something I pushed. It's like I'd show a video of an athlete jumping, and I'd be like, "What do you think?" And I'd be like, "Oh, they look good." And then you look at their forces, you're like, "Whoa, holy jumping! They're way different, right?" And it was like, and then I'd have videos of athletes that looked really off. You'd be like, "Oh, that looks brutal." And then you show the forces, and you say, "Oh, actually, the force signals are super clean, and they're pretty. It just looks a little different." And so it's like your eye is not something you can just trust to say it gives you the full picture. It's a small component of the big picture. And so, again, if you move the one step further, is this is more like putting a picture to movement in an objective way, like your eye would. So how you would see patterns of the foot through the air and ground contact times, you'd hear that, you'd see that, you'd hear or as the athletes running down the track, like great track coaches like can hear ground contact time asymmetries and they can see, but the average person's like, I have no idea what I'm seeing here. It just looks like a mess of stuff. And then you put an athlete on a field wearing equipment, like good luck. Like you can't tease that out because it's just too fast and too complicated. So this is really like kind of bringing an eye lens to human movement. Um, to your point, all those intricacies that you see and all those intricacies that you're kind of tuned into, that's what you can extract with this.
Nice, nice. So, man, I need to give Tom a shout out. He's the reason like we have a discussion about Plantiga like few days before, and he said I should ask all these questions because it's fascinating, man. This I
Yeah.
learned a lot, man. I
And it's
like it.
Tom, it's Tom from, and just so we're on the same page, it's Tom who I taught, right?
Yeah, yeah, yeah. Tom.
Yeah. So yeah, what an interesting story because Tom was in my strength training science course at the University of Calgary, and it was online. I think we were in COVID, and I have a couple of videos that I share of. I'm sure this guy doesn't mind me saying this. My good friend Jason Doomsday. He was a UFC MMA fighter, and he actually had a pretty good run for a while. And I have some videos of Jay Day learning how to do rudiment hops, and I use that to sort of talk about cueing and like jump strategies and how to like, if you see this, like what would you do sort of thing. And of course, Tom's like, "Hey, I know Jason Day," and so we connected online, and obviously, you and I also have a connection through Tom as well. So it's kind of cool, kind of cool.
Nice. It's a small world. I love this. I love this. So I'm gonna jump into the next topic. And I know recently, I think like a few months ago, you like launched a paper with Avatar, am I right? About
Yeah,
like ACL,
yeah.
like return to play from ACL. Can you like talk a little bit about that? Like, what's the difference between doing bilateral counter movement jump and single leg counter movement jump?
Yeah, sure. I mean, so the paper was it was Enda King, who's now down in at Aspetar, and he'd reached out and said that they were doing a special issue for their conference and asked if we would contribute something, and he just gave me the general title. He said, "Hey, could you do something on like, basically like explosive strength and ACL injury?" And I said, sure, yeah, happy to do it. And so we started in on a process of like pulling together some authors and some different people. Chris Bishop joined me on that. Chris is a good friend now. And obviously, him and I have done a bunch of different things together, but guy I really respect on, how to look at asymmetries and jump testing and all that. And, also had some other heavy hitters that I really respect, like Per Igard and Walter Herzog, and then my lab team, which I can't say enough about. They've been a huge. It's been a huge pleasure, privilege to be working with them over the past few years. So, Zach McLean, Nathan Von Mussel, and Nate Morris, who are sort of strength coaches and leading the charge in a bunch of different ways in the Calgary area. And so we throw together some ideas and essentially structure the paper by looking at the importance of assessing fast force, which we call explosive strength, and stretch shortening cycle capacity. So, those are the physiological words for, in my mind, being able to make, jumping, hopping, isometric testing for RFD, like all of these things that are kind of in the current lens of our world, bringing a bit of a background on the physiology of it, why it matters, how do we measure it, what are some considerations, and then at the end, Nate Morris prepped a section looking at how we train it. And so it was a really fun project, and it's got some really cool illustrations in it for anybody who wants to like use figures in their presentations or whatever. Like there's we put together some nice images that I think people will like. So long story short is we highlighted the literature and we looked at why fast force is important. So that's normally when we look at measuring, let's say, fast force capacity in a burst contraction. So rapid force capacity typically is measured as like a rate of force development or some sort of like time locked force. So force at 100 milliseconds or something that really is capturing the rise in force at the onset of a fast contraction. We talked about the physiology of that, some of the challenges in making those measurements, and then we went into a whole section on jumping. And so, the current push towards the incorporation of force plates into the daily training environment is probably one of the biggest changes I think has happened in the past 10 years in sport, where, those were pieces of equipment that before were only in labs. And now you've got, strength coaches and clinicians who've got force plates readily available to be able to look at their athletes' asymmetries and force capacities. And we talked about the bilateral and unilateral jumping. And I think the main thing to say is that um, so single leg jumping is our skill. It is something that we've now, like when I was working in Olympic sport before, we had athletes that were like speed skaters or alpine skiers who, like, we would train single leg jumping as a big part of the whole physical preparation plan. So they're good at it. And on average, if I brought a speed skater in and I said jump on one leg, it's like bread and butter, man. It's like they can make a single leg jump and no problem, super clean, good force signal, good control. Then you start moving into more of an athlete population that doesn't do that a lot. And so this could be like our collegiate sport system athletes here at the university where, they may or may not have been prepared to do these tests. And what we see is that it's just super variable. So your non-injured athletes are about as variable and asymmetrical as your injured athletes. Just because you might have one leg that you can kind of jump on and one leg that you're horrible jumping on. And it's not that you're injured, it's just that you're just not good at jumping on that left leg. And if I trained you and worked on it with you, you'd probably get better, but you can't do it at a baseline test. But after injury, we are sort of keen to think that single leg jumping is a core movement competency that you need to be able to restore. So, the idea that this could be the first time you've ever trained single leg jumping. But you need to do it. So what we like to say is that your single leg vertical jump is kind of a measure of your limb capacity. And so your limb capacity to generate, a big, big vertical jump height and to sort of demonstrate that stretch shortening cycle capacity. And it's also a movement that requires a substantial amount of movement control. So I think single leg jumping, the main difference with bilateral jumping is you've got a movement control factor that's substantially higher than a bilateral jump. And as you develop that movement skill, it really does tell you about the capacity of that limb to generate maximal muscle power and to sort of demonstrate that stretch shortening cycle capacity. Now you move to the bilateral jump, and the bilateral jump is obviously an easier jump to do. We train that much more readily. It's easier to learn. Almost anybody can learn to do that. And when you've got the two force plates, you can obviously see the fraction of the ground reaction force being contributed by both sides in the jump. And so that allows you to see some asymmetries, and it allows you to look at, obviously, in a more of a routine monitoring way, how these things may change over time, because bilateral jumping is pretty easy to do as a part of monthly testing, weekly testing, that sort of thing. The main thing that we see is that the more well-trained you are, the less well correlated these asymmetries are. So if you are high functioning, healthy, non-injured, generally we say that these asymmetries seem to be task specific. But the more you gravitate towards lower limb function, so now you're talking about, and by lower, I mean reduced limb function, like your limb function is worse because you're injured or you've got something going on, the more it seems like these asymmetries start to correlate, meaning that like if you're bad on the left side in a bilateral jump, you're probably going to be bad on the left side in a single leg jump. And you're also going to be bad on that side in a strength test. And you're going to be demonstrating longer ground contacts at times on that side when you sprint. So you can see that in a non-injured state, things are not really correlated. Like one could be better, the other could be better, and it's kind of random, which you would expect. Like you wouldn't expect to be perfectly symmetrical across everything you do. That wouldn't make any sense. Then you become injured, and it's like things start to become more of a pattern. So what I say is always like you're trying to detect a pattern of asymmetry, and you're trying to use that as a way to understand where are you going to target your training. So my advice to coaches is always to pick a bilateral jump, a single leg jump, and some sort of a fast hop. We prefer like a 10-5, the repeat cyclic hop test over the drop jump test, but pick a fast hop test. And then what that lets you do is to say, can I detect a pattern of asymmetry, which can allow me to monitor and track recovery? And can I identify any capacities where one side is a lot lower than the other side? And allowing you obviously to retrain that or to at least investigate why that is. So, there are some stark differences between the different types of jumping movements, I think, and they may not correlate when you look at healthy people, but they start to correlate more when you're injured. And my advice to coaches is to say, include all three jumps in your test battery, and it'll give you different information depending upon whether you're talking about a non-injured athlete or somebody who's coming back from injury.
Oh, that's awesome, man. So, uh, on the paper, you like talk a little bit about like what kind of metric you track on. I know you talk a little bit about like eccentric deceleration, am I right?
Yep.
And like, do you track eccentric P force?
I mean, this is a really uh I'm gonna try to answer this question with the most accurate information I can give. Um, Do I check eccentric peak force? No, I don't. But that's not to say that that's not to say that somebody out there may not say, "Hey, I've been tracking this forever and I see value in it." Here's what I would say. When you do a jump test, you will probably notice there are 70 to 80 kinetic variables that come out. And these variables describe different phases of the force time curve. And many of them are like going to be correlated with each other because they're kind of part of the same thing. And so it's like really hard for a practitioner to say, well, what should I choose? And because it's like, okay, where should I focus in on my outcome measures to understand whether or not something's different side to side? Your most obvious, easy thing to do is to pair up a forced time curve with high-speed video. This is like the most agnostic way. I get my force curves, I have a high-speed video, and I can look along the forced time curves and I can see where the differences are big. And I can pair it up with a video and be like, oh, it's this phase of movement where the person is demonstrating higher asymmetries. So it could be in this phase that we call the eccentric deceleration phase, which is after you're accelerating down towards the earth in your jump, you're dropping down, you have to basically generate a force to stop your downward acceleration. And so that force is to basically reduce your downward acceleration to zero so you can start to come back up again. You can see that on a video. And you may be able to see that certain parts of that movement phase are higher or lower asymmetries. So, you know, there's step one. The next step is to say, what are the main parts about jumping? Jump height, jump contraction time, and to some extent, how far you drop down. So you've got three things there that describe basically the summation of all of that kinetic energy, which is how high you move, the speed of the jump, and the depth of the jump. So I always like to say those are like your tier one measures. They're the ones that are you start there, you look at the differences there, you can tell almost everything you need to know about a really stark side-to-side difference with those variables. Then you go down one layer below that, and what determines my jump height is the area underneath the force time curve. We call that the impulse. So it's a mechanical variable that is the determinant of how high you jump, and it's the determinant of how you put the brakes on. So I say your next level of variable is to look at the impulse. And we look at the impulse in that braking phase and in that propulsive phase. So those two phases of movement, we can capture that. And now we're starting to get into a point, and this is really, really important, is to say we have to know the reliability of the measures. So, because we're going to start to enter into a zone where if the measures are super, super noisy, jump by jump or test by test, you're never going to be able to see the big differences that you need to, or the small differences that you need to see because the measurement error is too big. So your impulses tend to be a pretty reliable measure if you're using good protocols to set up a vertical jump test. From there, you're now into your tier three measures, and I would describe these as measures that describe the jump strategy. So these would be things like whole body stiffness. It would be maybe eccentric rate of force development. It might be force over 100 milliseconds after that braking phase. It could be your rate of power development. It could be the phase durations, like your eccentric and concentric phase durations in the vertical, like all those things are now describing the movement pattern. But, again, these are now kind of in a third tier. And then if we go down one final tier, that's usually where I get to what I call discrete time point measures, which would be things like peak force in the eccentric deceleration phase, peak force in the concentric phase. These are variables that describe a single instantaneous point in time over the course of a movement that takes about half a second. Now, your peak eccentric deceleration force, if it's substantially different, it probably also corresponds to, it's not just going to be that instantaneous point that's different. it's going to be an area that's going to be different in that curve. So it may very well correlate and be like, hey, actually, it does correlate super well with this, and I can extract that pretty easily and I can understand it. But you just would need to know that you should probably also look at the force time curves because you can imagine a scenario where the peak forces line up, but the curves are still really, really different.
Makes sense. I
So
like
that
that.
makes sense, right? So
Yeah.
I mean, just to summarize, you start with the curves and video. Tier one measures contraction time, jump height, and displacement. Tier two measures, which are now getting into some of the impulses that describe the performance, and they're really good for looking at asymmetry. They like literally determine performance. And then we've got our whole layer of measures that talk about the movement strategy. And then you get into the phase where it's discrete time points, which are also going to correlate with all these others. So, but the red herring would be peak force gets normalized. You're like, oh, cool, awesome. It's less than 10%. Sign off on this. My athlete's rehabbed and good. And then you look at the curve, you're like, oh my God, that instant kind of a key thing to keep in mind.
Yeah. Nice. I like that. I like that. So that's probably all the question I have for you today. So for those who are interested in what we're talking about today, I know you have like great online education, and me and Tom, we both we both like do that education, and it's really awesome. It's really fascinating. So for those who are interested in all those, where can they reach out to or find your education?
Yeah, no. So if you go to my website, it's www.jordanstrength.com, JORDAN. Strength.com. You can find all my courses. We have basically three courses, and this will be in the next 6 months, probably moving into more of a levels and systems. So our current one that we provide is the JSCEP system, which is our level two, which is comprised of the science of muscle strength and power, how to use force plates to assess asymmetries in mechanical muscle function, program design. We do a whole topic on eccentric training, and we have a final one that's on using R and becoming more scientific as a strength coach. Our level three is a course called Encoding Power. It's in person. So we partner up with Narax and we do it in Phoenix once or twice a year. And it's a 2 day event where we go in and we literally get right into case studies and we get right into how to use force plates, really practical. And that is going to lead into our mentorship program as part of our level three. And we're just in the process right now of developing our level one, which will be more of an introductory level course for people who, they want to learn and get into it, but they need a stepping stone to get to that more advanced level. So if you go to the core to my site now, the JSCP system and the encoding power ones are available. We're actually running an encoding power in-person course in May 17 and 18, I think, in Phoenix. And then my courses, we do some promotional discounts periodically throughout the year. But get access to the courses. There's online videos. It's NSCA certified for continuing education credits. And a sort of a periodic reach out to our people in our community to free events and whatnot. And the last thing I'll say just briefly is that we have a free content and download section so people can come and get all kinds of information for free anytime. So just go sign up and you can flip through and see what we got.
Nice, nice, nice.